So let's make a brief summary of what we have seen. Yesterday we started reviewing or learning something about conformal field theory, in particular about conformal field theory beyond 2 dimensions. So 2 dimensions is special. Why is 2-dimensional special? Because in 2 dimensions there are infinitely many coordinate transformations that correspond to Weyl transformations, whose effect is doing Weyl transformations. So if you have dz bar as your metric, you can change z to any f of z bar to any f of z bar, and you still get a conformally flat space. So you get any holomorphic function defines a conformal transformation in 2 dimensions. So you have an infinite dimensional group, and then from there on, the story diverges from the story in higher dimensions, where in higher dimensions, if you ask how many conformal transformations are there such that I do these transformations and the metric in flat space just changes by a conformal transformation, there are not that many. In 4 dimensions, there are like 15 such transformations, which are in 1-to-1 correspondence with the 15 generators of the conformal group. So it's a finite dimensional group, and that's one of the reasons why higher dimensions is harder than 2 dimensions, but there's still a lot we can learn about. Okay, so what was then the definition of a conformal field theory? I'm recasting it here in a slightly different way, which is absolutely equivalent to what we saw, but a bit more general, and it gives you a feeling of how I could define it if I wanted to do it more general. So let me more generally start with an Euclidean quantum field theory, which I define in the usual path integral way. So I have some path integral, and I have some sources J, some currents that I coupled the system to, such that when I take derivative with respect to these currents, I compute correlation functions. So it's a convenient object, it's a generating function, out of which I can get any correlation function. And you see here, I coupled this current to a given primary of dimension delta, and you can now understand easily what would happen if there would be other operators, other primaries. You would couple more currents. And what if the operators have spin, if they have some indices? Well, then I should couple to it a current that has spins, the opposite spins, right? If your operator has spins down, the current should have spins up, in a way to make some appropriate coupling of currents. For each primary operator of a given spin, I couple an associated current. And then the definition of a conformal field theory is the statement that a conformal field theory is one where this generating function is invariant and the rescaling and the local rescalings. Okay? Of course, O carries some engineering dimension, carries some anomalous dimension. So by invariant, I mean that I should rescale, of course, the source in a way that, together with a measure, that everything is invariant, but that's just dimensional analysis. Okay? So, and of course, as you see, if you add more sources, you would put more sources here, similar transformation laws for the scalar sources, and transformation laws that will encode the Jacobian, the rotation of the indices, if your sources would have spin. Now, this definition of a conformal field theory, in particular, when now I take derivative with respect to the sources to compute correlation functions, implies the one we saw before, yesterday, which was the statement that if a conformal field theory is one where correlation functions in 2 different backgrounds, but which are related by local dilatations, in other words, by Weyl transformations, one can translate from one to the other in a rather straightforward way by just multiplying by the local rescaling factor associated to each of the operators. Okay? This, on the one hand, this very general property implies in particular that when restricted to conformal transformations, correlation functions are invariant or covariant under conformal transformations. And of course, let me mention this because I think some people might prefer this other absolutely equivalent point of view, of course. If you prefer having invariance rather than covariance, as usual, it's rather straightforward to change from one to the other. You can write an equation like this that says correlation functions in some metric G are equal to correlation functions in some rescaled metric. But for this to be equal to that, that means that you redefine your operator, O tilde, to be, as I change from one space to another, not only I change the space, but I also change each operator by an appropriate factor. Okay? And of course, this is equivalent to that statement. The power of conformal symmetry was then explored yesterday to show that 2- and 3-point functions are totally fixed by symmetry and given parameterized by a set of numbers, which are the dimensions, and the 3-point functions, which parameterize the conformal field theory. And of course, we should then understand how in practice will we go about computing this and so on, and of course we'll discuss it in more detail. But the answer is you just compute the perturbation theory 2 and 3-point functions and read them off. Okay. Any question here? No, I'll continue the explorations of conformal field theory. The first thing I quoted here, and we are going to start with this in a second, is the conformal algebra. The conformal algebra, you see, this is the one you would write for Lorentz transformations in this embedding language of JAB, right? This is just a general Lorentz transformation. And then when you restrict the indices to this plus minus and so on to get to dilatation, special conformal translations, right? The way we saw that the conformal group was embedded into the Lorentz group, those Lorentz transformations split into these 6 commutation relations, which are the commutation relations of the conformal group. Okay? I'll come back to them in a second.
When we say that 2-point and 3-point functions are fixed by CFT data, like, is it only true when we deal with the correlation function in flat space? Like,
in flat space and in any space which is conformal to flat, because once you know them in flat space, now you can do a Weil transformation and derive what they are in other spaces. Right? Yeah. But otherwise, no. If you ask me, what about 3-point functions in a torus? Right? I take a torus and I compute 3-point functions in a torus, right? That's not just a Weil transformation of flat space. I have to rethink about that one. So in spaces which are flat or conformal to flat, that's when this statement holds. The last comment before we start the discussion per se is that please don't be confused with these pictures. That when we draw a cylinder, of course ADS is the full cylinder. We saw that ADS that sometimes we have a picture of ADS like this, where this radius is a row coordinate and it's filled. There's something inside, there are string theory inside. But the same picture holds when I'm just discussing the cylinder, the boundary of this surface, which is just some time, or it might be time, or it might be Euclidean, some distance, some vertical distance times the sphere. And of course I'm using the same picture, but when I'm discussing this going from flat space to the cylinder and so on, you don't need to think about ADS CFT and about ADS being inside or something. Of course, this language is almost begging to put an ADS inside, but you don't need to. It is just about discussing conformally flat spaces. Okay. Any question about what we have seen or other questions before we start?
So are you saying that ADS is including the bulk inside?
Yeah, ADS is including the bulk.
Cylinder is just the surface.
By cylinder I mean just the surface. So, and this is the kind of thing that we have been discussing yesterday. For example, yesterday we were discussing that when I have some points, so that I can think, imagine this is the origin, and I draw some circles. Right? Imagine I draw this picture, right? Where this was some distance r times some unit vector n, and this here is some distance r prime times some other unit vector n prime. Then we said that this is mapped to a cylinder where if I put an operator at the origin, I'm putting something here at minus infinity. And then if I'm putting something here and here, I'm putting something at some time tau, and then at some point tau prime, at some vector n prime, which points to a point in the boundary of this surface. Okay? And there was a map between the two. It was absolutely equivalent. I can really put an equal sign. We can really interchangeably discuss the left-hand side or the right-hand side, which is a statement of doing radial quantization, evolving from the center under this map where r becomes just the exponential of tau. In this picture, this is not the time, because everything is Euclidean. This is really an honest cylinder. D tau square plus sphere, no minus sign. Okay? So it is in this Euclidean picture that I wrote the commutation relations. So these are the commutation relations for the conformal algebra in Rd, not in R1, d minus 1. Okay, so let's discuss this algebra a little bit. So first here, these three relations here are trivial. This is just proper rotation of indices. This relations just code the fact that if I have any vector here, I can replace this kc by any vector vc, v with an index c. If I rotate them, the indices transform like this. I change the index by a b, or I change the index by an a. Okay? So that's just rotation symmetry. So these relations are just the same thing. So here, this relation and this, they are the same because both p and k are vectors. So it's just telling me that p rotates like a vector. And this one is like two vectors. It has an index c and an index d. So either I rotate c or I rotate d. So it's just twice these relations. Okay? So if I put here a new relation for a current with an index c, I mean, everything, it's trivial to write when it has rotations. Just saying things rotate. Okay? Do you agree? Now, these ones here are more interesting. Okay? These things here are more interesting. This here tells me that, as we discussed yesterday, that P is like a raising operator, meaning that P mu acting on O, which would be d mu O, has dimension delta plus 1. It increases the dimension by 1, whereas K decreases the dimension by 1. So K would be a lowering operator. Okay? And finally, they commute to the dilatation operator, which we are going to discuss in a second. Okay. So, any question here? Let me just see something here. Okay. This we did. Okay. So let's now remind you or discuss something very important, which is called the state operator correspondence. Which you could discuss purely in Euclidean space, but I do think this cylinder picture is very useful to think about what's going on. So let me try to tell you a little bit. So, as we said, if we are here in RD, we can put a point at the origin. So this will be the origin. And then we put some points more separated from the origin, and then we consider this radial evolution, and so on. Now we consider these concentric circles. Okay? So this is the origin at x equal to 0. And if I think of this radial evolution, the way I would like to think, which in the cylinder picture is very natural, is by saying that I'll put some boundary condition at the origin. So on the boundary condition at the origin, which is the same as saying that I put some operator at the origin. I'm putting some operator at the origin, which is like inducing some boundary condition. Now this operator can be 1, can be the identity, in which case it means don't put anything, put just a number 1. Or it can be an operator. I can put a primary operator there, or a descendant, or something. So I put something there. 1 or an operator. And I think at putting that thing as a cat. So I'm thinking of radial evolution, so I evolved from a cat. And then at infinity, here at infinity, I have a bra. Like I'm evolving from a state, from the past to the future. Okay? So in the cylinder, that's easier to think about. In the cylinder, after all, let's be a bit more explicit, what are we doing? Suppose, for example, I just consider an operator. Suppose we just put an operator here at O1 and an operator here O at x2. Suppose at the origin for now, okay. So yeah, so at the origin, first I put 1. So I don't put anything, so I just insert 1. So what does it translate here? So what am I computing here? Well, I'm computing the correlation function phi at some vector n1 tau 1 and phi at some vector n2 tau 2, right? And computing the path integral in this cylinder where I evolve in time. Okay? But what is this? What does the path integral compute when we do time evolution, right? So I remind you, so how does this path integral work when I compute expectation values? Okay? So let's do first say quantum mechanics. And you compute expectation value of position at T1 and position at T2. Right? So what happens when you derive your path integral? You discretize things, tac, 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 tac. Then you put at T1, you put the operator. Then you continue discretizing time, and then at T2, you put the operator. And then you continue discretizing things. Right? So in the path integral, when you see Q of T1 times Q of T2, what you are computing is the time-ordered product. Right? So in path integral language, the way you translate from canonical to path integrals compute time-ordered expectation value of fields. Right? So if I want to translate to the language of saying that in my cylinder, I start with some vacuum, and I go to some vacuum, right? Because at minus, I'm preparing, this is operator 1, this is operator 2, and I evolve from minus infinity, so here I have some vacuum state. And then I evolve for infinitely long Euclidean time, so it means that in the future I project into the vacuum state. Because path integral evolution for infinite Euclidean time creates the vacuum. So we have the vacuum in the past, we have the vacuum in the future, and here we should act first with operator 1 on the vacuum, and then with operator 2. Or in other words, we can put this symbol of time-ordered expectation value, and then we can put phi of n2 tau 2 times phi of n1 tau 1, even though now that we were careful in putting phi 1 to the right, we don't need a t. Okay, we can put the t just to remind us it was not by chance, and I'll put a hat to indicate I'm doing canonical quantization. These are now operators that act on the Hilbert space in the cylinder, and they act on the vacuum and produce some state. Okay? And of course, these are just the usual operators at some time. So these guys would be just e to the tau 1 times the Hamiltonian operator at n1 and tau equal to 0, e to the minus tau 1 times the Hamiltonian. Okay, this operator here, and similarly for the other phi. Okay? Okay. So what is happening here is that we are starting with our vacuum here. We are evolving the vacuum, we evolve the vacuum, and then here we acted with, so here we had the vacuum, and now here I have some state psi, which was the result of acting with the vacuum on the vacuum with operator phi 1. Okay. So it's in this sense that we can think of cat and bra in both pictures. And we can also put now at the origin, more generally, I can put at the origin some primary operator O, and at infinity I can put another operator O. So let's say I put O1 at the origin, O n at infinity. And then what we would say is that the correlation function, while here I will discuss a correlation function O1 at 0 dot 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 On at infinity, right? This quantity is equal in this picture here to saying that Well, now if I put the operator at the origin, which I can think that I'm putting it away from the origin and taking the limit as it goes to the origin, I can put some limits and deltas and epsilons if you want, but okay, let's, of course, that's trivial. So we just make it go to the origin. So now, instead of producing the vacuum, we produce a ket O1, which is again the limit of phi1 acting on the vacuum as phi1, the time goes to minus infinity. Now, instead of going to the vacuum, it goes to the bra On, which is the limit of taking the point On and making it act on the vacuum upstairs. And in between, we have the time-ordered product of the other guys. Let's suppose they are ordered, and we would have O2, O, and minus 1 acting as operators on the vacuum. If now, in this picture, so now if, okay, I should draw again. Where now in the picture we are putting, we are thinking about the most general case, which of course includes, let me repeat again, you can think that the vacuum is a particular case where the operator I put at infinity or at the origin is 1. So if I put 1, then what I call ket O1 becomes vacuum, and ket On becomes vacuum. Right? But otherwise, what we are doing here is saying here I prepare some ket O1, then I have some operators O2, and then say O3, and then here I prepare the ket O4, for example. So this would correspond to the picture where n equals to 4, a 4-point function.
Is the ket O1 is equal to O1 acting on that?
Yes. 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 That's true. Okay. With some limit, you have to put the operator close to the origin, take some limit as it approaches. Okay.
Why is the limiting process so important? Like, why do we immediately define the O1?
The limiting process probably for. The limiting process is important to have some well-defined limit if I'm thinking of my operators like this. So if I take my operator like this, right? If I propagate this operator to minus infinity, right? So if acting on the vacuum, this term gives 0. But this term here going to minus infinity will give me some number, some big number. So I want typically to multiply by e to the minus tau times the dimension of the operator, and then send tau to infinity to kill this term. This is not going to be important at all. But I just want to, but sometimes, okay, to do it completely rigorously, you should put. For example, this quantity here is equal to 0, the way I defined it, because if you put an operator at infinity, the correlation function decays. So when I write such formula, I mean that I multiply by infinity to the power delta n and take the limit when infinity is infinity. Right? Then this is finite, for example. Okay? But this kind of thing is, I'm being schematic here, right? Okay. So let's see. So once more, so let's write some formulae translating things. So in one picture, we write things like saying, if I have some operator O at the origin, say, or first generically, if I apply a dilatation to an operator O, so this column is the picture what we would think in RD. So if we act with an operator D on O, what do I get? I get minus I delta times O plus, depending on the position where O is, x dot dx acting on O, which is dilatations. So if the operator is at the origin, this is not there. If I'm at the origin, because x is 0. And we get that the dilatation acting on O gives minus I times O. In the picture of the cylinder, in the picture where I think in the cylinder, R times S d minus 1, this equation translates into saying that if I act with dilatation on my ket O, I get minus I delta times the ket O. Okay? This minus I disappears as we go to proper, as we if we were to weak rotate to Lorentzian, in which case this time would become a real-time evolution and the energy would be the energy of the states on the sphere. Okay? But right now we are doing Euclidean, so Euclidean evolution, e to the I Hamiltonian gives a decay rather than giving a phase. Right? Okay, so e to the minus id gives e to the minus delta tau, which is the decay of exponential functions that we were seeing, for example, when we were studying yesterday, and we had 1 over cosh t minus t prime to some power delta. This exponential decays because we are doing Euclidean. It becomes an oscillating phase if we were to do Lorentzian. And as I do Lorentzian, this tau goes to it, and the dilatation would go to what I would normally call an Hamiltonian evolving. But of course, I might use both interchangeably, because it's the same. So time evolution in the real time evolution, when I say that I put a theory in the sphere, is related by weak rotation to Euclidean evolution in this honest space cylinder. Okay?
I'm a bit confused about the discussion here. What is it special for the R cross vector when we discuss about the state? Like, can we write down the same equation for the RD, please?
This is the same equation in a way, right? It is just the way I would implement in a path integral language, right? Action on an operator is the commutation on the operator, right? If I translate action on operators to actions on states, it is just the usual translation of notation. As I said in the beginning, most of this discussion I could describe it totally within flat space, not most, everything, provided people were willing to accept that when we quantize a system, we don't need to do an evolution like this in slices, we can do a radial evolution of the system. Right? So what we are doing is doing a radial evolution of our path integral, saying I evolve my path integral, and the way in my mind I should think that I discretized my fields, my time was in concentric circles and not in a time evolution like that. Okay? If you allow yourself to think in that way, you can forget about the cylinder. I just like the cylinder because once you go to the cylinder, you are doing the usual quantization. You evolve things in time, you act with operators, you continue evolving. It is just standard quantum mechanics. Okay? So then there's nothing fancy there. So in this picture, we also add that K acting on O is equal to 0. This defines primary operators. And then we add that P acting on O is derivative of O, and this defines descendants, this generates descendants. Okay? This generates descendants. And in this picture, to translate into the statement that when I take a primary, I act on the primary and I get 0 for a primary. And the descendants, and in general, I have, on the other hand, the Fock space, which is when I have the operator, O, and then P mu acting on O, P mu, P nu acting on O, and this is the structure of my Hilbert space in the cylinder. I have a bunch of primaries, and for each primary, I have the primary, the descendant, the second descendant, the third descendant, and so on. Okay? So in the cylinder, we have usual quantum mechanics with this Hilbert space, where this guy has dimension delta, this guy has dimension delta plus 1, this guy has dimension delta plus 2, and so on. And we have such thing for each operator. Okay? I don't know. How do you write this for each operator? Okay? The union to the next thing with another operator O prime. Right? So this is your Hilbert space. So this is what you can put at the origin and and then you evolve it in time. Okay. Finally, something that is convenient when we have a quantum mechanical system is having some notion of Hermitian conjugate, of asking how do I map a cat to a bra. Right? So if I want to think I have a cat and a bra, and I act on the bra, but you say, oh, but in equivalent you can act on the cat. Right? So how do we think of Hermitian conjugation in this picture? Well, Hermitian conjugation, let me just remind you, so Hermitian conjugation, what should be the Hermitian conjugate of P, for example? Any guess? Huh? What should be, if in this language, how should I think of the Hermitian conjugate of P? Okay? How should I think of the Hermitian conjugate of K, the Hermitian conjugate of D, the Hermitian conjugate of M? Okay, let's think a little bit. Let's try to answer that and think how should we think? So, in a Lorentzian theory, we have that physical observables are such that when I have some observable A at some time t, the observable is Hermitian. Right? That's the definition of a physical quantity in quantum mechanics. I have some physical observable. This observable is Hermitian. This implies that in Euclidean, in the Euclidean picture, when I apply dagger, I get A of minus tau. Right? I'm just reminding you of standard things that I think you saw probably, right? But if not, it's obvious, right? Just change t to I tau and you get this. Okay. But you see that, remember, R was e to the tau. So tau to minus tau is an inversion. The transformation that flips tau to minus tau is an inversion that flips R to 1 over R. So this A of minus tau is nothing but inversion A of tau inversion. Nothing but conjugating my operator by an inversion. Okay? So if we put tau equal to 0, we conclude that A dagger equal I A inversion. And this is how I should think if I want to think of an operator in the plane and think of it, which is very clear. What I'm saying is that you have an operator at the origin, and conjugating it sends the origin to infinity. So it flips exactly a cat into a bra. So what happens when I conjugate K dagger? When I say that K dagger is when I say that P dagger is equal to inversion P inversion. But that's nothing but K. Right? What about K dagger? Well, K dagger is nothing but P. D dagger is minus D, and M dagger is M. For example, D dagger is minus D is just saying that as you dilate points close to the origin, if you are dilating them, they are becoming more squeezed at infinity. Because you are pushing people there, right? So now they are squeezed there. Okay? So as a check, we can, not as a check, but we can compute, for example. Okay, not as a check. Okay, this is it. So, again, just as a simple exercise, we can compute what happens when I act with a dilatation operator on a state with P mu, which was P mu acting on O. Okay? And let's do this simple exercise. This is equal, even though I anticipated the result already, to the commutation D on P acting on O plus P times D acting on O. D acting on O is minus I delta times O. P acting on this commutation relation is minus I P mu. Right? And here there is P mu. So in total we get minus I times delta plus 1 times P mu on O. So this is the state we start with. So we conclude that indeed the dimension delta was increased by 1. Okay, it's just the usual thing, how these harmonic oscillators work. Now, as a similar exercise, we could now consider the following more interesting application, which is to study the operator P mu O that we computed now its energy, and ask what's its norm square. Well, the norm square of this operator will be O, and now that we know how to conjugate P, we write K mu times P mu times O, because K is the dagger of P. And now I can use the algebra to commute P and Q, right? So I can replace this by the commutator without any cost, because K on O is equal to 0. Do you agree? So I can replace without any problem K on P by the commutator. K on P by the commutator, we wrote there, gives me 2I delta. Okay. So this thing here, this commutator, gives me 2I times the dilatation operator, right? Plus the rotation, some rotation stuff. But the rotation stuff, if we act on a scalar, gives 0, because scalar is invariant on the rotations. So this term might drop if it's a scalar. I should raise the blackboard, right? Okay. So we are almost done. So let me try to continue here. And we conclude, therefore, so if you follow, so K with P we could replace by commutator. Commutator is 2ID. D acting on O gives minus I delta. So it's equal to delta times the commutation, maybe a factor of 2, but that is not important, times the norm of O with O. And this is positive, of course. It's a norm. So it means delta should be positive. Okay? So we just derived that delta should be positive, which is, of course, what we expect for a unitary theory, that the energy should be bounded from below. And okay, in particular, we derived that requiring that this norm is positive, we concluded that the dimensions of scalars in a CFT should be positive. Any question? Okay, but in fact, you can ask, could I do better now that I have this Hilbert space picture and I have these operators? Could I compute the norm of funnier operators and get better constraints? So now you can ask, what do I gain if I impose that the norm of P mu, P nu, acting on some operator O, is bigger than 0, or bigger or equal? Right? So now I have P, P, K, K. I have to commute several times. So I leave it as an exercise. And you can check that you get that delta is bigger than D over 2. Let me just check. I mean, I often do a mistake here. But I think it's that here. No, D minus 2 over 2. So delta is bigger or equal than D minus 2 over 2. Okay? And for scalars, you cannot get a stronger constraint. But it tells you that there is a bound on, if you have a unitary conformal field theory, there is a bound on the dimension of scalars. The dimension of scalars must at least be bigger than D minus 2 over 2.
What's the difference between the ranges of these indices? Do mu and nu run over just the first and last term? And A, B, the Latin and the...
No, there's no difference. No difference.
There's no,
no difference.
So there will be a factor of the dimension of space-time coming from the delta mu in that term?
Good point. Yeah, probably yes. good point. Yeah, indeed. Yeah, indeed. It was a bit too fast. Indeed, this was the delta mu nu, and as you are pointing out, there is indeed a D. So here there is a 2 and a D missing, but these are all positive stuff. So the conclusion doesn't change. Delta is positive. Yes?
When we use the commutation relation there,
yes,
we have the rotation in it.
Yes.
In the O.
Yes.
You mentioned that the O is invariant, so shouldn't it be like the M acting on O, it's still O, and then it becomes...
No. Invariant means that M acting on O is 0. Because when you have an invariance, it means that the group element, e to the omega times m acting on O gives O. So it means that m kills O. When an object is invariant under the symmetry, it means that the group elements don't change it. In other words, it means that the algebra elements kill it. Right? Because e to the I generator should give 1. So it means generator gives 0. More questions? Or comments? Skeptical remarks? Very good. So by the way, actually here it might look a little bit like dark magic, because now it looks like we are taking things out of the hat that will be harder to get in the original picture of flat space. Now that we have this, now we say, oh, now I have this Hilbert space, I can impose norms to be positive, and it starts to look like I could derive this, that it's not so obvious how I would establish in RD. Right? It starts now we start to gain something, it seems. Right? That is not so obvious, right? To address your question. So in the beginning we said we can do everything in flat space, but now if you see, probably at this point you cannot see right away how we would derive this result. In fact, it's not something that is discussed much, so I would like to comment on how to think of this result from the RD point of view directly. Okay? Which is actually something very, very cute and general, which is called reflection positivity. And reflection positivity is the statement that when you have a quantum field theory, an Euclidean quantum field theory, and suppose I consider correlation functions of something, of some operators, for example, it can be a 4-point function or a 5-point function, and suppose I consider something which has a symmetry with respect to some plane. For example, it could be a picture like this, where this picture could correspond, for example, this picture could correspond to computing a correlation function O1, O2, O3, O4, where these points are distributed like this in a symmetric way. Okay? So there is a symmetry here. Okay? But it can be anything. You can put here some Wilson loop and Wilson loop here. You can anything that is symmetric in the Euclidean conformal field theory. Okay? And then the claim is that this quantity is positive. And that's very simple. Why is it positive? Because if I think from the point of view of an Euclidean path integral, I'm evolving from the vacuum, evolving, hit some operators, evolve. I prepare some bra here. And I do the same from the past, and I evolve, I produce some cats. But because there is a symmetry, they are really the same. So they are positive because this is nothing but a norm. It's a scalar product. And as such, it should be positive. I'm just evolving it symmetrically from bottom and top. Okay? So now, let's apply this logic and consider the following. Let's consider a line or a plane. So this is a plane, okay? And let's consider an operator here and an operator here, which is symmetric. So let's say this is minus x and this is x, okay? And then this correlation function is 1 over x to the 2 delta. Okay, fine, it's positive, but we gain nothing. Okay? But now, let's consider that instead of putting O here, let's not put O of x here, let's replace O of x by O of x minus O of x minus some epsilon. In other words, now I'm going to consider the case where I put some operator, a linear combination of 2 operators here and here, and here a linear combination of 2 operators here and here. So I compute now the correlation function. You see, it's O of x minus O of x minus epsilon. And what's on the other side? O of minus x minus O of minus x plus epsilon. You agree? That this is totally symmetric. It's invariant on the reflections of x to minus x. And I'm just exploring this vertical direction, nothing else. Okay? And now it's no longer obvious that this is positive, because now this is 1 over, there is this term, this with this, which gives, sorry, 1 over 2x to the 2 delta. Then there is this one with the last one, which gives plus 1 over 2x minus 2 delta, minus 2 epsilon to the 2 delta. But then there are the cross terms, which give me minus twice 1 over 2x minus epsilon to the 2 delta. Now it's no longer obvious that this is positive. There's a minus sign there that's becoming very dangerous. And now you can, I leave it as an exercise, you can easily convince yourself that this quantity is positive. So this quantity is positive implies that delta is positive. Okay? So we derived the weakest condition that we had here, that delta needs to be positive. Okay? So this is how we'll think about this condition here. And as a fun, there is now you could try to play a funny game, which is the game of saying, how can I make it harder and harder for my quantity to be positive? How can I consider a correlation function which is very non-trivial that it is positive, where I'm really putting plus signs fighting against minus signs? So you can try to think of the optimal configuration, and the answer is the following. So now let's explore the fact that we have various dimensions to work with. So I'm really putting a plane. And let's consider that here I have my operator. Okay? And now consider the following. Consider this operator minus these neighbors in all its directions. Okay? So consider insert here O of x minus 1 over d, or okay, let's maybe 1 over 2 to the d, sum of O of x minus epsilon mu, and you sum over all the directions mu in this hypercube. You see? This depends on the dimension. The hypercube, how many sides you have, depends on it. And now when you compute correlation function with this, with its mirror, you have many positive signs, but many, many negative signs. And you can easily see that this is bigger than 0 if delta is bigger than d minus 2 over 2. Okay? And that's how we rederive that bound in this language. So, of course, as I promised, you can work with both languages. But for example, this one, I think you will agree that the cylinder is a bit easier. But this one also works, of course. Okay. So now, let's go on and discuss the next very important thing in a conformal field theory, which is the operator product expansion. Or people call it OP. Okay? Now, the OP is the following statement. It's the statement that if I have my operator here, O1 at the origin, and my operator here, O2 at some point x, okay? And then there might be some other operators, but I don't care about it. The claim is that I can imagine a sphere that encircles them. And say that from far away, if I look from far away, well, I can replace this by some operator OK at the origin, right? But I should sum over everything, over all operators K with some constants or some coefficients, we'll be more explicit about it, C1 to K. Okay. It's like when you have some charges from far away, it looks like the total charge plus some dipole plus some quadrupole plus something like that. Okay? So it is just the expansion, seeing this operator from far away, I should be able to replace it by some effective operator at the origin. Now, from this picture of the cylinder, it's totally clear what we are doing. What we are doing is just saying that if I have my cylinder, and I have my ket O1, and then I have my operator O2, and after acting with O2, I got some state psi here, right? But psi is a state in the Hilbert space, so it's a linear combination of CK OK. So this relation follows, and there's really not more to it. Okay? Conversely, another way of saying is I generate some state psi, okay, here. After acting with O, I generate some state psi. And now suppose I evolve it backwards with my Hamiltonian. So I evolve it backwards until time equal minus infinity, and I get some state at minus infinity. Right? That state at minus infinity corresponds to putting some boundary conditions, which corresponds to putting a local operator in the other picture. Right? So here in this picture, I say that I'm doing my path integral. I reach this sphere. Now I have some state psi prime. Now I undo the path integral and go back, and I get some boundary condition there, which corresponds to putting some operator there. But some operator there is some state there, which is a linear combination of kets. Okay? So it's an intuitive statement, but it's more than an intuitive statement. It's one that just follows from the isometries, from the fact that we have this possibility of doing this radial evolution. Okay? Right? So this defines some state here, and this state, then, when I do evolution backwards to the past, I get some state in the past, which corresponds to an operator again at the origin. An operator at the origin. Okay? So more precisely, the way I should write is say that O1 of x, or O1 at 0, O2 of x, okay, it's equal to a sum over all operators I can put with some coefficient that could depend on x in general, OI at 0. And if I'm summing over all operators, I can say that I sum first over primaries k, and for each primary, I put here OK at 0. Okay, no, not here. Sorry, for each primary, I have some ck of x plus ck with index mu1 of x times d mu1, which would implement a descendant, plus ck with index mu1 and mu2 of x d mu1 d mu2 plus dot dot dot, and all this stuff acting on operator OK that then I put at the origin. Okay? And in this way I say that any two operators I decompose into the Hilbert space that we discussed above, where I sum over primaries, and for each primary there is a family of descendants. Any question? Notice that this picture, I'm telling that I can replace two operators by another operator, right? Inside the correlation function. I can look at two operators and replace it by a third one. What's the radius of convergence of this expansion when I write this expansion like this? Well, it's easy to see. Suppose I have a third operator like here, which is here. right? Definitely what I can do is, unless, if this circle is before this operator, I can do this. Otherwise, I cannot. So the radius of convergence, which is also clear from this picture, is I start evolving and I can undo, and this expansion breaks down as soon as my circle hits the next operator. So this defines the radius of convergence of the OP. If my position x is bigger than this radius, it's not fair to replace the 2 by 1 because there is another operator inside the sphere. So I cannot just take those two. Okay.
This holds for any field theory, right? Like, this is not just something specific to... Is this something specific to CFTs? Because I can always evolve back my problem.
It's something specific to CFTs in the sense that if your theory is not a CFT, this evolution can generate singularities as you do the evolution to the past. So why are we guaranteed that when we start, so I say that I have an operator, I generate a state. Then I act with O2, I generate another state. Now I have some state. Now I said, now I evolve back and shrink to the origin and I replace that by an operator. How do I know that when evolving back I don't hit some crazy singularities and start developing singularities? And the reason is, I know I don't, because I'm evolving it. What is this evolution? I just have some Hamiltonian, which is some constant matrix, and I'm just multiplying by e to the I times some constant matrix, which is my Hamiltonian, right? Because the Hamiltonian is just some matrix that acts on this Hilbert space, it's some constant matrix, and if I multiply some state by e to the I times Hamiltonian, it generates no singularities. In other words, if I decompose my state into the various eigenvectors of the Hamiltonian, just multiply each eigenvector by a phase. So nothing special, nothing singular can happen. But if your Hamiltonian depends on the scale, which is what happens when you have a theory which is not a CFT, then you have no guarantees. Then the evolution is more like evolving some complicated differential equation, and you are not guaranteed that you cannot reach singularities. So it's not obvious that if you have some points, that you can create a state and then undo the path integral. So you can, because you have an isometry, which, or in other words, because you have some Hamiltonian which is static. It's not dependent on the radius where we are. Which in the cylinder means that you have an Hamiltonian that is time translation invariant. So it's not true that for any theory I can go to the cylinder. If I would go to the cylinder fictitiously for a theory which is not conformal, I should keep in mind that there's no reason for this to be time translation invariant. Because time going to minus infinity is like exploring UV, and tau going to plus infinity is going far away from the operator. So from the point of view of inserting the operator, things are very different if I'm close to it or far to it, if there is some intrinsic length scale in the problem. Okay. So now, let's see what can we tell about this OP. So let me anticipate, I want to finish this logic today, that our idea now is, well, but if I can take two operators, put a sphere around them and replace them by one operator, can it be that I can have a complicated 4-point function, 5-point or 6-point function, and put a bunch of spheres and reduce my problem to 2- and 3-point functions, right? Because if I have 4-point functions, if you replace two of the operators by a third one, now I have a 3-point function. But 3-point functions were fixed by symmetry. So our goal is to reach this claim that I said at the end of last lecture, that the conformal data is actually enough, and that we'll be able to get even the higher point functions. Okay, so that's where we are aiming, and I want to finish this logic today. So that's my goal. Okay, so let's go on. And so to use this OPE, we would like to learn more about what are these constants here with indices. What is this C mu, this C mu1 mu2, this C mu1 mu2 mu3, and so on. Okay? So the intuition is that these things are related to descendants, and we know that descendants should be trivially related to primaries, because a primary and the descendant is just a derivative of each other. So it's natural to expect that perhaps I can have one unknown, which is related to the primary, but that the other ones will be fixed by symmetry and related to the primary. And that's what is indeed the case. So to see it, let's start with our 3-point function, and let's consider a 3-point function, O1, O2, OK. Okay? Where this is at 0, this is at x, and this is at some position y. Okay? And this is equal to C1 to k, as we saw yesterday, times 1 over what? X which is the difference between these two to the power delta 1 plus delta 2 minus delta k. The distance between the last and the first is y to the power delta k plus delta 1 minus delta 2. And the distance between 2 and 3 is x minus y to the power delta k plus delta 2 minus delta 1. Okay? So this is fixed by symmetry, and this is what it is. Okay? And this is equal to, okay, this factor here is equal to, okay. So let's go on. So this is equal to 1 over absolute value of x to the power that is there. I don't want to change it. Delta 1 plus delta 2 minus delta k. Absolute value of y to the power 2 delta k times, I'll write an equality and you can see if you agree or not, 1 minus 2x dot y over y square plus x square over y square. So you see what I did here? I just computed x minus y square to the power delta 2 minus delta 1 minus delta k over 2. Okay, the over 2 is because I computed x squared, so I have to divide by 2 because there's no squares there. And then I just reorganized terms and brought some powers of y inside the second term. That's why there is no y squared here and so on, and that's why the powers are as they are. Okay? Very good. So we just rewrote things a little bit, because then this factor here, I'm going to expand it at small y and say that this is 1 plus delta 1 plus delta 2 minus delta k times x dot y, which is x mu y mu over y square plus dot dot dot. Okay? Do you agree? Okay. On the other hand, so this is on the one hand. On the other hand, we can use the OP here. Right? On the other hand, we can use the OP there. And when we use the OP, what do I get if I use the OP? I get that this correlation function is equal to a sum over the primaries k, and then to a sum over how many derivatives I act, which can be from 0 to infinity. Okay? Some c k, so I sum over primaries k prime, some c k prime with index mu1 up to mu n, right? And then derivatives that act with to this operator, okay, which I can write as derivative with respect to y mu1, derivative with respect to y mu n, acting on the correlation function OK prime of 0, OK of y. So I just use the OP to replace the two operators by the operator OK prime. This thing here, there is a mistake in this formula. I'm going to fix it in half a second. This thing here, as we saw, is just orthogonal. Delta k k prime times 1 over y to the power 2 delta k. Right? Do you agree? So it's only a function of y minus 0. The derivatives were normally with respect to 0. But because it's only a function of y minus 0, I can trade it to derivative with respect to y. But of course, then there is a minus 1 to the end that I should pay. Okay? So this minus 1, okay, it's trivial, but okay, just this is d dy versus taking derivative with respect to x and putting x equal to 0. Okay. So if we now expand this out, we see that this is ck of x, right? I just expand this out and I compute these derivatives explicitly, and I get, when n is equal to 0, I get ck of x times 0 derivatives, so just 1 over absolute value of y to the power 2 delta k. And then as I expand, I get plus ck mu of x times one derivative of this, and one derivative gives me 2 delta k y mu divided by absolute value of y to the power 2 delta k plus 2 plus dot dot dot. Okay? Okay, now things nicely work out. Let's see how they work out. Why do I say that they work out? Because you see, as I expand the 3-point function, the two sides should agree. So this term, which is a 1, right? The 1 here comes multiplied by this power of y, which is the same power of y. Right? So it tells me that this factor here, right? This factor is this ck. This ck is equal to this factor. Right? But now, what about the next term? The next term, according to this, should come with a y mu divided by y with an extra 2. And indeed, when I go here, I see a y mu and an extra y with a power 2. So the y dependence perfectly matches, right? And now I read off this stuff here. Right? And this stuff is the difference. This stuff is what is this, so namely this thing. So the summary is now identifying all powers. Okay, I'll write here. We conclude the following. We conclude that ck of x is equal to c1 2k, the structure constant, this CFT data, times this power of x. X to the power delta k minus delta 1 minus delta 2. ck with index mu of x is equal to c1 2k, absolute value of x to the same thing. Okay? And then times delta 1 minus delta 2 minus delta k over 2 delta k x mu. So let's see why did I do some step? Right, because when I compare both, so you see I have to divide by this 2 delta k, and for this to match, I should have what I wrote there. Okay? And you easily see that you could now go on and say that C with index mu1 up to mu n for a primary k, but associated to the descendant, should be equal to C1 to k, the same power here, delta k minus delta 1 minus delta 2. And then here there will be some tensor B, mu1 up to mu n, where there's this is just some vector B mu. But the point is that this tensor is totally fixed by symmetry. It is just obtained by expanding further that equation and comparing more and more and more terms. Okay? So what we conclude is that all these guys, there is the first one, which is not fixed by symmetry, but which is fixed by symmetry up to the 3-point function. So it's related to the CFT data that we already computed. Right? So if you know the CFT data, if you know the 3-point function, you know the first one for the primary, the first OP. And once you know the first one, everyone else is fixed by symmetry. So there really is nothing new there. Okay? So let's go on. So the conclusion is that this is the conclusion. It's this thing here. And what other comments I want to make? I want to make the following comment. Look at the power of x, and suppose x is small. What is this telling you? It's telling you that the bigger the delta K, the more irrelevant this is. Which is of course intuitive. I'm just saying that I take two operators and I expand. An operator that have lots of energies start becoming irrelevant and start decoupling, and what's important in the OP is to take the first few low-lying states. As with anything in physics, when you have some energies, you take them lowest states, they are the important ones. Very energetic states, they are just suppressed. Okay? So good. So now we have all the tools we need. We understood how to take two operators and replace them by one. So we can now use it and in the 4-point function to get rid of, to go from 4 to 3-point function and write a full result. Okay? So let's do it. So I want to finish it. I know I'm going a little bit over time, but I don't want to really come back to this tomorrow. So can I continue here? Can you see here? I mean, someone complained that here it's hard to see. Is it hard or it's okay? Or do you prefer that I raise there?
Either one.
Either one? Okay, so I'll go on here. So let's go on, and now let's say that I have a correlation function O1 of x1, O2 of x2, O3 of x3, O4 of x4. Right? So now, the idea is I can replace these two operators. I can do the OP on these guys. Right? And write, so please check this follow because I'm going to be a bit fast. And write the following. I replaced OP, so I sum over all primaries K. Okay? Then there is this number C12K, which appears, which is an important number, which appears in the OP. This is this 3-point function or structure constants or OP coefficient. There are many names for it. Then I will leave some space here, and then there is some power of x that we have here to the power delta K minus delta 1 minus delta 2. Sorry, I should be careful. It's not x now. Now x is this distance. It's x2 minus x1. Right? You agree? Yeah. Then, on top of that, because I have the primaries, I have my b, mu1 up to mu n, which is a function of x2 minus x1 as well. And I have to sum from n equals 0 to infinity. Right? These guys, they act on derivatives with respect to, I'm going to replace this by an operator at position x1. So derivative with respect to x1, mu1. Derivative with respect to x1, mu-n. And then they act on what? Well, I replace these operators by OK. So they act on OK at position x1, O3 at position x3, and O4 at position x4. Right? But this is fixed by symmetry. It is just C, 3, 4K times something fixed by symmetry. So I will divide here by C, 3, 4K, because then there is no C here. It is just 1 over some power. Right? So now this is 1 over a bunch of power. Something simple that is also fixed by symmetry. But because I divide, I should multiply it here. C, okay, I'll write this, K, 3, 4. It's the same. Okay? Do you agree?
Yeah.
And now, all these things, all this complicated square bracket, you see it looks complicated, but you agree that this thing is something that is totally fixed by symmetry. All ingredients here are fixed by symmetry. So this is a function. You compute it once, you suffer a little bit, please compute the next 1 million terms there, get all these b's, act with all this derivative, see what it resums into, compute once, save it, and you don't think about it anymore. Right? So this is a function. As good as Bessel function, sine, cosine, just normal. Right? So this function here, this square bracket, which is totally fixed by symmetry, is what is called a conformal block. It's a known function, it's a conformal block. Tomorrow I'll write explicit expressions for it, but the problem is implicitly well defined. So it's a function f that depends on the deltas, on this delta i's, on delta 1, delta 2, delta 3, and delta 4. It also depends on delta k of the exchange guy. And then it depends on x1 up to x4. Okay. And even though it's a bit simpler than that, okay? But it's a known function, f, which sometimes I will simply write this as say it's fk. But it's a known, it's known, something that we can take it as known. So what we conclude is that if I have a 4-point function, this 4-point function I can write as a sum over k, and I just take two operators and fuse it into some operator k. So I draw this picture. 1, 2 became operator k, and I sum over k, and then I go to 3 and 4. See k going into 3 and 4 with some function fk. So fk is a function that what this picture is saying is, if you want to compute a 4-point function, take two operators, form a primary operator k, and let that operator k decay into operators 3 and 4. But you say, well, but there is primaries and there are descendants as well. What about the descendants? And I'm saying, well, this function f is resumming the descendants. It's telling you that you can now exchange towers of operators at the same time. You don't need to just exchange one operator, one element of the Hilbert space. You exchange tower by tower. Like when you write sums as sums over spherical harmonics, which are the relevant stuff to some things that have spherical symmetry. Here we have conformal symmetry. So things organize themselves in multiplets, in this case in conformal multiplets, where I have a primary and its descendants. So there better be functions that will tell me how to relate the various elements in this multiplet and how to resum them all at the same time. It would be unreasonable if I would have to sum primary by primary. So these conformal blocks are the are to the conformal group as spherical harmonics are to the rotation group. They are the objects that resum these multiplets. And the analogy is even stronger if I had been a little bit less devious in the sense that I highlight here an important detail, which is that I never mentioned spin. I never mentioned that even when I have scalar operators, in the middle I can have operators with spin, and tomorrow I'll start the summary of the lecture by telling you that there is a very small modification that I have to do, because when I sum over operators k, they don't need to be scalar operators. So this sum over k, to be totally rigorous, later will become a sum over operators of some dimension delta k and some spin lk, and I will have to tell you that the conformal block also depends on the spin. Okay, but it's a very minor modification. Conceptually, I don't think it's crucial to understand the global picture. So the conclusion is that indeed, if you give me what is then a CFT is a set of C's and deltas. Because if you give me C's and deltas, I get everything. Okay? So now you ask, okay, can I give you a list of C's and deltas? Can the deltas be the date of birth of, I don't know, the gods of the Greek mythology or something? And the C's can be something like that. Will it work? And the answer is no. As we will see, a CFT is a set of deltas and C's. But there will be power constraints that tell me that furthermore I cannot just choose whatever I want. And that's what we will study tomorrow. I think I need one more lecture. Can we have an extra lecture? Because I lost the one on Friday, and if I want to, I need 2 lectures for Wilson loops, and I clearly would like one more lecture for CFT. Can we schedule one more lecture? Maybe tonight or something like that. What do you think?
Tonight, the science students have a mandatory academic integrity workshop. So
Colloquium.
Oh,
I don't know.
like 12 o'clock.
Nobody can lose that.
Or is it unreasonable? Gang, should I have consulted with you first? Is it, I would like to finish this conformal block stuff and tell you a little bit how in N=4 we would apply this kind of technology and go about checking it in string theory to try to close the loop with ADS. But then I would still like to have a little bit of time to tell you how to think about Wilson loops in ADS-FT in particular, because it helps introduce this sort of non-local observables that have some similarities to kind of things that Freddy will do. So I think it will be nice to still have 2 lectures for that.
During this tutorial?
Do you have anything for tomorrow's tutorial?
Yeah, but I was assuming that, yeah, I do.
We can do the tutorial during another time.
Yeah, we can reschedule tutorial sometime.
Yeah, if you could reschedule the tutorial for Friday afternoon,
Sure.
that would be perfect, because I am a bit late with so the last tutorial I would like to be about computing minimal area for the Wilson loops. So then it makes total sense, and it's a good tutorial to finish, and it's a kind of computation that's also useful for the entanglement stuff. So it will be a good way to finish, but for that I need to reach that point in the lecture, so it will be perfect if it could be after the last lecture.
So tomorrow's tutorial time we'll have lectures?
Yeah. I would propose that if people are happy with that.
And then we'll schedule tutorials another time.
And then the tutorial will be on Friday at any other time that you want on Friday.
Do we still have a second homework?
Up to you.
Oh.
Why not? I can always prepare something.
What?
Okay, is someone against this idea? I mean, the other option I can skip also. Would you like to discuss Wilson loops? If you like to discuss Wilson loops yourself, I can just talk and complete.
No, when it reply?
But it's on Sunday. Sunday evening. I can do Sunday morning.
Let's not make your day.